Hi guys, today we're going to talk about differentials. Alright, so this is a new topic for us, but it's going to be in the context of tangent lines that we'll be looking at them. Alright, so something new with something we've talked about before. Differential. Well, when we hear that, that reminds us of the word difference, right? So differentials, we're just going to be looking at differences. That is what happens when we change our x to our y. Alright, so when you see differential, I want you to kind of think difference. We're talking about some change, some incremental change in our x and the effect it has on our y. Incremental Alright, so for that we need to recall a couple things. We need to first recall the equation for our tangent line that we've been using right along. Alright, that's f of x minus our y value at the point of tangency equals our slope, or the derivative at the point of tangency, times x minus the x value of our point of tangency. Alright, and that's for our tangent line at the point C, f of C. What we're going to use differentials for is to estimate our values of our function near the point of tangency. Alright, so I'll put that in with a little asterisk here. Use differentials to estimate the y value of our function near the point of tangency. Alright, another word for this is local linear approximation, and we'll talk about that more a little bit later. Tangency. Alright, coming right up is the formal definition from your book of a differential, and we're going to look at how that comes into play here in just a moment. So, your book's definition of a differential in math speak says let y equal f of x, so y is our function, f of x, represent a function that is differentiable on an open interval containing x. Remember, differentiable means that it's continuous and we can take the derivative on that interval. The differential of x, denoted dx, that's some incremental change in x, is any non-zero real number. The differential of y, denoted by dy, is equal to the derivative of the function times dx. So all this is saying is we've got some function y equals f of x. We're familiar with this. Then when we write the derivative of that, we would normally have it written like this. And if you remember, when we looked at the left-hand side here and we saw that dy dx, we talked about how our derivative is like a rate of change at a point, right? It's our instantaneous rate of change. So we related that to the slope of a line, or change in y or change in x. That's all we're doing with differentials. So we're saying for some change in x, how much does my y change? So look at that. I have to bring my dx to the other side so I can compare the change in my y, my dy, with the change in my x. So all we're doing here is a little bit of algebra. Alright, this right here is telling me about my change y, and this guy over here is telling me about my change in x. So that's all differentials are. They're talking about our change in values. Alright, so that's just to get us started. Now we've got two facts that we recall. First, we're going to use this relationship here. Alright, that we've just established. And we're also going to use our equation for a tangent line. We're going to play with that a little bit. So we're going to use this. And we'll be doing an example with this shortly, so just bear with me. Alright. Alright, so let's say we have this prompt. It says, estimate the value of the square root of 16.5. Alright, so differentials are important here because right off the top of our head we can't say what the square root of 16.5 is. So if we use differentials we can find an estimate. I'm going to write it out in terms of our something we know, which would be the square root of 16 in this case, alright, and in terms of the in general problem. So in general, we're looking for some value of a function that's close to one that we know. That's all that says. That's f of x, we're looking for some value, some y value, that's close to one that we know, that x. We know the x, we don't know the one once we've added the slight change. Alright, and that's the same as saying, well, it's the one we know, plus some change, something we don't know. And we can use our substitution of the fact that we just derived above, whoops, sorry, to say f of x plus the derivative times that difference in x, that change in x. So when we're looking at this problem, we've got when x is 16, we know what the square root of that is. So let's say we've got over here 16 plus our change in x, our part we don't know, our 0.5. So we know that the square root of 16, but we don't know what's going on here with that 0.5. So that's going to be a question mark for right now. Before we can do that, we have to figure out what our derivative is. So our original function f of x is the square root of x, alright, or x to the 1/2. Our derivative of that, which I know you all know how to find, we pull down the exponent and we make it 1 smaller. So that would be the same as saying 1 over 2 square root x. Alright, if you need help with that, see me. So where we have this question mark now, we're going to replace that with what we just derived, 1 over 2 square root. Alright, in that spot we're going to put our x, which in this case is 16, what we know, and then we're going to have times our differential, our difference in x, which was 0.5. So we know that square root of 16 is 4, plus, alright, we've got 1 over 2 times 4, and then this 0.5 is just like 1 over 2. Alright, then what do we have going on here? Well, let's break it down. We've got 1 over 8 and 1 over 2. 4 plus 1 over 16. Alright, normally I don't allow this. We're going to just convert this over to a decimal. right? And it comes out to 4.0625. So this is what we use differentials for. So we use them to estimate a value when we can't compute it right off the top of our head, but we know a value near it. All right, so I want you to try this one. And this one. Okay, so that's 2 for you to try. And once you've given that a go, all right, go ahead and give the second video a gander and see what the solutions are. Thanks.